This video is a brief introduction to the TRIPS Python library. TRIPS stands for Trajectory Redistribution in Phase Space, and this library is for radiation belt particle tracing and magnetic field analysis. This is a simulation of a 70 megaelectron-volt radiation belt proton drifting around Earth performed using TRIPS. Its orbital motion can be quantified in terms of 3 adiabatic invariants. In TRIPS, a particle trajectory is a high-level Python object that is instantiated by passing a 6-dimensional state vector, but rather than position momentum, this state vector is in terms of the particle's 3 adiabatic invariants and their corresponding phases. A simulation like this can be launched using a configuration file. Amongst other things, it specifies the species of particle, the electromagnetic field, which in this case is loaded from a file and stored on a numerical grid, and the adiabatic invariants, mu, equatorial pitch angle, and L star of the particle/particles. We can also tell TRIPS to re-evaluate a particle's adiabatic invariants and respective phases at the end of a simulation. A key capability of TRIPS is evaluating a particle's instantaneous L star, and this calculation is performed according to the following steps. Firstly, the field is frozen in time. Then, the magnetic mirror field strength, Bm, is determined from the local pitch angle of the particle and the magnetic field strength at its gyrocenter. The conjugate mirror points for the particle are then determined, represented here by the blue dots. The quantity I is then calculated along the portion of the field line traced between these conjugate mirror points. The field line is then traced to the surface of Earth, which is represented by an ellipsoid surface mesh. The algorithm then steps to a neighboring longitude and searches up and down a meridian for a field line with the same value of I between conjugate mirror points, where the field strength is Bm. The foot point of this field line provides the next point in the contour, and the contour is extended this way around the surface of Earth. Certain elements of the surface mesh are encompassed by the contour, as you can see here. When this object, representing Earth's surface, is constructed, it pre-calculates the magnetic flux through each surface element of the mesh according to the International Geographic Reference field model. We can now consider the surface elements encompassed by the contour and sum the magnetic flux contributions to find the total magnetic flux, phi, encompassed by the drift orbit. This in turn allows us to calculate L star. This whole calculation can be performed by instantiating a drift shell object, passing a gyrocenter location, local pitch angle, and time, and then calling the solve method, passing a magnetic field object and Earth's surface object. And we can use a function called solve trajectory to launch particles from the drift shell. TRIPS also includes a function to find and return the last closed drift shell for a given magnetic field object. To demonstrate some of the useful methods associated with these high-level objects, we'll launch another simulation, this time initializing particles from L star of 4. We'll also include 2 particles at different drift phases by specifying the different drift phases as comma-separated values normalized between 0 and 1. We'll specify the maximum duration of each trajectory as 1000 seconds, but then tell the simulation to quit after a single drift orbit. Taking a look at this new simulation, we can see these 2 protons initialized from the drift phases that we specified, then drifting around Earth and undergoing some scattering. This scattering primarily occurs around magnetic midnight, and we can demonstrate this by using one of the methods of our drift shell that allows us to interpolate from its solved contour at a given magnetic local time, or MLT. Here, we're using that method to interpolate a point on the surface mesh at an MLT of 0. Then, we're using a method of our field object that allows us to trace the field from this point to conjugate hemispheres until it intersects with the surface. TRIPS also includes a function to analyze field line curvature. It returns the radius of curvature along with other parameters at the point along the field line where the radius of curvature is smallest. Using these methods, we can produce the plot on the left, which shows 3 curvature parameters evaluated along field lines at different MLT on the drift shell at L star equals 4. This includes the radius of curvature in the top subplot in units of Earth radii. The red dot in each subplot corresponds to the field line that we traced at MLT equals 0. We can see from the top subplot that the radius of curvature has a minimum around this location, and it results in field line curvature scattering, which explains why our particles become non-adiabatic. Continuing our solution, we can make this plot clearer by using TRIPS to extract the guiding center trajectory from the solution file. TRIPS can simulate particles in electromagnetic fields which are either static or time varying. It can also solve particle motion forwards or backwards in time. In this last example, we simulate an electromagnetic disturbance caused by the arrival of an interplanetary shock, using this empirical model from Leotel for the electric field perturbation. This model disturbance, which is based on a real event, led to the inward acceleration of radiation belt protons that drifted in time with the shock. Here we see the simulated trajectories of two radiation belt protons, one of which drifts in time with the shock and one of which does not. The paper shown on screen gives more details about how TRIPS was used to investigate the redistribution of radiation belt protons during this event. This has been a brief overview of the TRIPS library. Thanks for watching, and please see the GitHub for more information.